Okay, so chapter 5 is on discrete probability. There are 4 sections. We will cover sections 1 and 2 today. Probability distributions, just in general, what are they? That section is just a couple slides long. And then we will talk about how do you find mean, variance, standard deviation, and expectation from a probability distribution. Okay. And then on Thursday, I plan on getting into the binomial distribution and some of the other types of distributions that are also discrete. There's one called Poisson, there's one called hypergeometric, one called geometric, and one called multinomial. So we'll look at each of those separately. Okay, so a random variable is a variable whose values are determined by chance. Okay, that makes sense. We have these random variables that we deal with in statistics. But a discrete probability distribution, it consists of the values of a random variable that can assume the corresponding probabilities of the values. So I know that's a little bit wordy, but basically it has random variables. So we're going to have a variable, and those variables will be discrete numbers, okay, separated, countable, okay, and we're going to also record their probabilities. And ultimately, a discrete probability distribution can be represented in a table. So almost everything we're going to do and that you're going to see is going to have a little table. And we usually put the table this way instead of vertically, which is interesting because in algebra, we usually always have like x here and f of x here or y values here, right? But with probability, they always put them horizontally. So these would be our x values in the first row, and the second row would be our probabilities, so p of x. Okay, so those are the outputs for each variable. So we put it into a table. Each of these are discrete, they're separable, so we'll have separate numbers and they're countable. So there will be a starting and stopping point. Okay, it doesn't go on forever. So we have a discrete distribution. Interestingly enough, the sum of the probabilities of all the events in the sample space always add up to 1. That's a review concept, right? All of the probabilities always have to add up to 1 or 100%. So all of these probabilities down here in your distribution, those will always have to add up to 1. And each probability has to be between 0 and 1. You can never have a probability that in here that would be a negative probability. You can't have a probability that's like 1.3. Okay, all the probabilities have to be between 0 and 1. Okay, so here's an example of a probability distribution for rolling a single dice. So the outcomes, they're discrete, right? When you roll a dice, the outcomes are what? 1, 2, 3, 4, 5, and 6. And then what are each of their probabilities? 1/6, right? It's a 1/6 chance that you're going to get a 1, a 1/6 chance you're going to get a 2, a 3, a 4, and I usually kind of separate these. But these are each different probabilities. Now, what do you notice? What do all these probabilities add up to? 1, right? 1/6 plus 1/6 plus 1/6, 6/1/6 is 1, okay? So all of these add up to 1. Now I always have someone go, oh, so every time you do it, you just count up how many of these are and write 1 out of how many? No. Depends on the distribution. Sometimes these probabilities are all different numbers. They all happen to be the same because with a dice, it's equal chance, right, of everything. But with a discrete probability distribution, you will notice that these always add up to 1. Now, I ask you to construct a probability distribution for the sum when rolling 2 dice. So right below here, I want us to do another one, okay? And we're going to put x and p of x. And my question to you is, what are the outcomes of the sum when we roll 2 dice? So does it start at 1? What does it start at? When you roll 2 dice, what's the lowest number you can get? Snake eyes, which is a 2. Good. So we can get a 2, we can get a 3, and then keep going till what's the highest number that you can get when you roll 2 dice? 12. That's double 6s. Now here's the interesting thing. Each of these is not 1/12. Each of these is not 1/11, okay? How many total outcomes are there when you roll 2 dice? Remember that sample space that you used in the last chapter? 36, right? So we got to think of how many ways we can do this out of 36. Now snake eyes, the only way you can get snake eyes or get a 2 is if you get snake eyes. You get a 1 and a 1, right? So this has a chance of 1 out of 36. And the only way you can get a 12 on 2 dice is by rolling 2 6s. So that also has a 1 out of 36 chance. But all these other ones have different probabilities. So let's think about it. Rolling a 3, what are some of the outcomes that would give you a 3? A 1 and a 2, and a 2 and a 1. So there's 2 ways you can get a 3 out of 36. How many ways are there that you can get a 4? 3. A 1 and a 3 and a 1, or a 2 and a 2. So there's 3 out of 36. Now let's go back from this side. How about an 11? 5 and a 6 and a 6 and a 5. So there's 2 out of 36. And how about a 10? You think there's 3? 5 and a 5, 4 and a 6, 6 and a 4? 3 out of 36. Now, if you're thinking it's going to follow a pattern, you are right. Follow the pattern into the middle. Add them all up, make sure it adds up to 1. So the numerators need to add up to 36. Cool? Okay. I like this one. It's kind of pretty, to be honest with you, in mathematical sense. It's a pretty distribution. This is the chances that you would get each of these. It does add up to 36. Each of them have different weights. If I was a betting person, what would I bet? 7. You're going to bet that you're going to roll 7 because that has the most chance. Now, usually fractions need to be in simplified terms. We didn't simplify these because it was easier to add up and figure out that it add up to 1. But if you were looking at a true probability distribution of this, you would want the 2 out of 36 to be simplified down to 1 over 18, okay? And the 6 over 36 to be simplified to 1/6, okay? Fractions always are simplified in math class, right? So we should probably simplify all of those, but I don't need to for the sake of our time right now. But what I think is this is really kind of a beautiful distribution, actually, kind of cool. But the question is this. So on average, what would you think you would get? If you rolled the dice 500 times and you wrote down all those numbers and averaged them, what do you think your average number would be? You told me you would expect to get a 7. You would bet on a 7. That has the highest probability. Do you think that's our average? Do you think that would be our average? We'd get 1s and 12s, and right? Yeah. In fact, 7 is not only the most popular, but it is also what we call the mean of the distribution. And I'll show you how we get that, but 7 is actually our mean. On this one, back up to this one, what do you think on average you would get if you roll a dice? They all have equal chances, but on average, what do you think we would get? So you roll a dice 100 times, you write down all the numbers that you get, and you average those. You add them up and divide by how many they are. What do you think you're going to get? Someone take a guess. Turkey Valley? I'm looking at you guys right now. Someone take a guess. What do you think? What would you get on average?
Any of them?
Okay, you would get any of them, but if I took all of them, let's say I rolled my dice 100 times, and I add them all up and divide by that, what would the average be of all of those numbers? You're going to get some 1s, you're going to get some 6s, you're going to get some, right, 2s, some 5s. If I average them, what am I going to get? They all have equal weights. What happens when you average these 6 numbers? What's the average of these 6 numbers? 3.5, right. Happens to be in the middle of this distribution because these are all equally weighted. So 3.5 would actually be our average because we'd sometimes get 1, we'd sometimes get 6, right? And as I look at this, because these are all equally weighted, that's going to be my expected value is that I would expect to get about 3.5. Well, which is interesting because you can't roll a 3.5 on a dice. So if you were thinking that, that's okay. But that actually is the average of this one. And the average on this one is 7 because these are equally weighted going all the way up and down. Now, we're not going to have to look at a distribution like that because we're going to have different distributions that don't always match up. But we are going to be able to put these in our calculator. What do you think would go into list 1 in our calculator? We're going to have to put one of these lists of numbers in list 1, one in list 2. Which one goes in list 1? Which one do you think goes in list 2? If it was your common sense, what would you put in list 1? The x's, right? And what would you put in list 2? The probabilities, right. It's like x and y, list 1, list 2, right. Okay, so this stuff's going to go in list 1, this stuff's going to go in list 2, and we'll use that here in a second. Okay, so here's a different one. This is tossing coins. The number of heads that you could get if you toss, this is tossing 3 coins. If you toss 3 coins, how many heads could you get? You could get none, or you could get 1 head, right? 1 or 2 or all 3. Now, how did they come up with these probabilities? Why is it 1/8, 3/8, 3/8, 1/8? Well, we need to go back and think about the sample space. So remember what the sample space looks like when you toss 3 coins. Head, 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 right? You could get 3 heads. Tail, tail, tail. 2 heads and then a tail. A head, then a tail, then a head. Tail, then 2 heads. 2 tails and a head. A tail, a head, and a tail. And a head and 2 tails. So now as I look at the sample space, how many outcomes are there? 8, right? And my probability distribution, no heads. The chance that I'm not going to get any heads, that's only this one, all 3 tails. That's 1 out of 8. 1 head, there's 1 head that's this one, and this one. That would be 3 out of 8. 2 heads, there's 3 out of 8. And 3 heads, that's when you get all heads, that's 1 out of 8. Okay? And as you look at this, we could make a graph. So this is a kind of an interesting graph. Does anybody remember what this one was called? What type of graph you would call this? What name you would give it? Instead of the frequency over here, we put relative frequencies, which is fine. These are like the probabilities, right? Or the percents. This would be like the percent, right? So these are relative frequencies. And we have the x values here, and we have boundaries, and we have bars. What was the name of that graph that has the bars on it? Okay, it starts with an H. I feel like a total failure as a teacher because nobody remembers anything from Chapter 1 or Chapter 2. It starts with an H. Histogram. Okay, this is an actual histogram. And it is a graph of this. It's a histogram using relative frequencies over here instead of frequencies. It uses the class boundaries along here. So negative 0.5 to 0.5, you know, as these boundary points for each bar. All right. Okay, I'm going to show you this slide real shortly, and then I'm not going to make you stay on here very long because, as you know, very rarely do we actually use these formulas, okay? Because we have a graphing calculator or even just basic calculator that I told you about where you can put stuff in lists and it will calculate the mean the standard deviation, and then we can find the variance by squaring it. But if we were going to do it out longhand, this would be the formula. So you have to take each x value, multiply by its probabilities, and then add them all up. That will give you the mean, okay? And I want you to understand that mean is actually the same thing as expectation. So I see that the directions up here say mean, variance, standard deviation, and expectation, but you notice on the slide there's no expectation, okay? That's because the expectation or the expected value is actually the mean. In statistics, when I ask, what do you expect to happen? What's the expected value? That's the same as the mean for a probability distribution. So expectation, expected value, those are all the same thing, and we'll see that on the next slide. Okay? So as I go to the next, it says the expected value or expectation is the theoretical average of the distribution. The expected value is the mean. Okay, and right here it says E of x. That's another way of saying expectation. You won't see that notation really at all, but that's the same as the mean, which is the same as doing all of this. Now this looks like a lot of mumbo jumbo, but it's saying you're going to add up all of the x's times their probabilities. Faster way, throw them in your two lists and run one variable stats, right? We're pretty comfortable with that hopefully now. So since we have a probability distribution, we are going to be putting them in our lists and running our one variable stats, and it will automatically do this for us, okay? Where our probabilities are now going to be our frequency list, okay? The probabilities will be the frequency list. So I write that all out right here. The mean is the same as the expectation. I put list 1 needs to be your x values. Those are the outcomes. And list 2 has to be the probabilities. And you're going to run one variable stats, list 1, comma, list 2, or if you have the table that comes up, you'll put list 1 and list 2. List 2 goes in as the frequency list, okay? And then the mean or expectation, that's going to be x bar, okay? That looks like this on our calculator. It's the very first one, right? That's the mean. We're comfortable with that now, knowing that x bar is the mean. The standard deviation, and I couldn't put in the notation into this PowerPoint. I can in my Excel documents. I probably should have just done it and then taken a picture of it, but it doesn't transfer. So I put sigma sub x. On our calculator, it looks like this. Sigma sub x, like that. Remember that one? That's standard deviation. And then to get the variance, we take the entire standard deviation number and we square it. Okay? So that's the fastest way to do these and the most accurate. Because if you're going to use those formulas, you're going to have to do each part separately, make a huge table, and it's not very accurate, okay, nor efficient. So we want accuracy and efficiency. So the variance, you'll take the entire standard deviation number and square it. So you're going to take sigma sub x, that whole thing, and you're just going to square it. Okay? So you will be required to know how to do each of those. And let's go ahead and look. Oh, before we do that, rounding rule. Their rounding rule says the mean, the variance, and standard deviation should be rounded to one more decimal place than the outcome. What I noticed is on some of your homework ones, they don't care. They'll tell you what to round to. So a lot of times on the homework it says round to 4 decimal places. Then you need to round to 4 decimal places, okay? So in general for reporting out, this is kind of how you round. You round to one more, but I noticed that like a lot of times on your homework it'll say round to 4 decimal places. So then go ahead and round out to 4 decimal places. Okay, so we're going to find the mean or the expected value, the variance, and the standard deviation of the number of spots that appear when a die is tossed, okay? And for most of the problems, you're going to be given the picture, and remember what the picture looked like. The picture was this. When we roll one dice, it's just this table, 1, 2, 3, 4, 5, and 6, and each of these had a probability of 1/6, okay? So we need to find, according to this problem, the mean or the expected value, the variance, and the standard deviation. So I'm going to write mu equals, and remember that's x bar on our calculator. And then we're going to have to find standard deviation, that's sigma, or sigma sub x. And then we're also going to have to find variance, which is sigma squared, or sigma sub x squared. Okay, those are all the same thing. So we're going to grab our calculator, and in list 1, which we get to that by doing stat, edit, and in list 1 I want you to put 1, 2, 3, 4, 5, 6. And in list 2, those all need to be 1/6, exactly 1/6, so you have to type in 1 divided by 6, okay? 1 divided by 6, and do that all the way down. Unfortunately, it's not like Excel. You can't just do a fill down. You got to actually type them each in, but it doesn't take that long. Okay, once we have everything in list 1 and list 2, we're just going to go ahead and run our one variable stats like we're comfortable with, where this is going to be our frequency list. So stat, go over to calculate, one variable stats, and then if it just shows the regular screen, you're going to do L1, comma, L2. If it shows this screen, you're going to do L1 there, and for your frequency list, you're going to put L2. And go ahead and calculate. What do we expect to get? 3.5. Okay. What is our mean? 3.5. What is our standard deviation? 1.7. And what is our variance? It's this whole number squared. Don't just take 1.7 and square it. You need to square this whole number. So some of you are probably remembering, oh yeah, she showed us a trick how to square the whole number. I'll show you again so you don't have to type it all in and write it all down. Okay? So, but let me write down what the mean was. The mean was 3.5. The standard deviation was 1.7. And to get this, we got to square the standard deviation. So we're going to have to take that whole number, that 1.707825128, and we square it. But I don't want to type that all in. So fast way again, if you remember, okay, is it's under variables. So if you hit this vars button, there's an option for statistics. And if you go down to statistics, you should be able to find the standard deviation. It's number 4. And then you just hit the squared button on your calculator, which is right here above the log button, and hit enter. And there's the exact number squared. So it's rounded to one place is 2.9. Now you might get lucky a couple times if you type in 1.7, that rounded number, and square it. You might get 2.9, which we did that time if we round it. But sometimes it doesn't. Sometimes it's off by a tenth or even a couple tenths because of what numbers come behind it. Okay, so you need to be very careful, make sure that you use the whole number. So I prefer you do it this way. You do it this way, you might get off by 1. Plus, you're not. If you do it this way, you're not going to get it rounded out to 4 places. Okay, so 2.9 rounded to 1 decimal place would be our variance. Okay, so here's a probability distribution that comes from data. This is not theoretical probability. This is an actual experiment. So they did a survey. They surveyed a bunch of people, and they found out that the number of trips of 5 nights or more that American adults take per year is in this thing. So 0 people, or 0 trips is 0.06. 1 trip of 5 nights or more per year is 0.7. So it looks like the majority of people, right, take 1 vacation a year pretty much. I call this a vacation. If you take a trip and you're gone for 5 nights or more, that's a true vacation, right? And it looks like most people do 1 of those. Do you realize that 20% of people, supposedly from this survey, do 2 of those a year, okay? And only 3%, they do 3 of those a year, okay? Must be fairly wealthy to do that, okay? You can't go on 3 5-day trips in a year and not have a little bit of money. I guess it depends on where you're going. If you just go to Fontana and set up a tent for 5 days, you might be okay. It might not cost you too much. All right, and 4 trips, four of these a year, 4 vacations a year, 4 trips of 5 days or more, 1% supposedly does that. Okay, so which one's the most popular? 1. But we're not going to say that that's the expected value. We actually need to put this into our list, okay, and average it. And you can notice that these are not all weighted the same. So we don't just want to average these. We want to use these as our weights, okay? So make sure that you put those all in. This is going to go into list 1. And this one is going to go into list 2. And in a second, I'm going to call on someone to give us our mean, someone to give us our standard deviation, someone to give us our variance. So I want everybody to participate, please. Put these in your list, run your one variable stats, and then we'll record them down. So the mean is the same as x bar, your standard deviation, and your variance. Oh, we forgot to check to see if this is a true probability distribution. Do all those probabilities add up to 1? Because if they don't add up to 1, then we're missing something in this data. But they do, okay? 0.06, 0.7, 0.2, 0.03, and 0.01. Those sure do add up to 100%. So. Okay, Emily from Turkey Valley, you have the mean. Wesley from Starmont, you have the standard deviation. And Shannon from Starmont, you have the variance. Go ahead when you're ready.
The mean is 1.23.
Okay. And if we're going to do the rounding to one place, we'll just go 1.2. But yes, it is 1.23 on our calculator.
0.6 for the standard deviation.
Okay.
0.417 for the variance.
So round it out to one decimal place on that, 0.4. But yeah, it was 0.4171 when we took the whole thing. Perfect. Okay. Okay, so on average, with all of these different weights, people take 5 trips of 5 nights or more is 1.2, right? 1.2 times per year. Okay, here's one more. It says find the variance and the standard deviation for this. Let's read the actual data. First, a talk radio station has 4 telephone lines. If the host is unable to talk or is talking to a person, the other callers are placed on hold. When all lines are in use, the others are trying to call will get a busy signal. The probability that 0, 1, 2, 3, or 4 will get through is shown in the distribution. So the chance that nobody's going to get through is 0.18. Okay, that means that all the other lines are full. 1 person is 0.34, 2 is 0.23, 3 is 0.21, and 4 people is 0.04. Okay, even though there's 4 telephone lines, we got people on hold, right? Got other people on hold. So here's your probability distribution. Hopefully these bottom probabilities add up to 1. They all look like they do. Okay, go ahead and find the variance and the standard deviation. And Andrew from West Central, you have the we always do the standard deviation first on our calculator, so you get the standard deviation, and Evan, you get the variance.
It's not 1 decimal place.
Yep, 1 decimal place.
1.3.
okay, for the variance. Standard deviation?
1.4.
That's not what I got.
1.4.
Yeah, I didn't get 1.4. So you got to double check your numbers in your lists. Okay, these should be in list 1, these should be in list 2. Make sure that you didn't have a typo in there. It should be 1.1. It's 1.123343224. I'm just double checking my numbers there. All right, let's move on to the next. Oh, the binomial. All right, we're going to take a little break. So